Recording is rolling. Welcome to Tuesday. So you guys remember yesterday, I did a real fast crash course on thermodynamics. We'll do a similar thing today for, I'll call this materials, but here's a breakdown. Here's a bunch of physical principles you guys can see dealing with material properties. Before I get into this though, I want to do a couple things. One is to remind you guys that AP exams come up about 5 weeks. So here's AP's daily live review. So you might be taking a few AP classes, but for physics 1, looks like it's going to be at 5 o'clock p.m. Eastern time daily. I guess go to the site. Oh, here you go. Join us at youtube.com/advanced placement. I'm pretty sure I did put this link on Google Classroom as a link. So anyway, there it is. We're making a video recording anyway, so a couple ways to get that. Also, we switched my screen over. I know I showed this yesterday, but keep reminding you guys, because you guys are taking a college class, and this is a good transition class to college. When you guys are in college, there's a lot more independence on your part to figure out, well, how much do I need to study for any particular class? Right? And so kind of get a taste of that now. There's a bunch of resources here, a bunch of daily videos like per unit, right? Scroll through these units. There's practice exams here. There's you got like on-demand review. And then myself, just over last weekend, I uploaded a bunch of assignments that I created out of multiple choice questions from the past. And so just opened these up. I was waiting until I got about this time of the year. So now unit 7 progress check multiple choice B. Eventually I'll pick. Oh, looks somebody's already started this one. There's a tentative due date here of 4/22. That might get pushed back, but a lot of these other ones I put the due date like the day after your actual exam. So 5/13, that's the day after the whole thing. Practice exams. There's multiple choice questions from each session. There's some FRQ questions. Right? So lots and lots of practice. Want to review? There you go. That is there. Right. The other thing I have to mention before get going too far is Val pointed something out to me yesterday that I went home and double checked, and I was like, oh, yep, there is definitely something wrong with that quiz that you guys just turned in. Actually threw out one of the problems. Oh, you know what? Before I tell you guys which problem I threw out, maybe I should ask you guys, do you have a strong guess which problem I had to throw out? It was number 7. Yeah. Wait, did I tell you guys that yesterday? All right. Well, yeah, it was number 7. Okay. There were 2 problems with number 7. One was kind of a technical calculator problem, and one was actually pretty fundamental. And made me realize, oh, I have to go back and change the numbers on this because, right. So the sort of technical problem was 6 and 7 were really just the same scenario. There was this fender bender car crash, and you had to figure out, well, it's the post collision velocity of like the other car. And then I said, well, now there'd be anytime you have a collision that's not perfectly elastic, so not this. There's going to be some transfer. So here's a counterexample of what I'm saying. It's like the rare counterexample. There's going to be some transfer of mechanical energy to non-mechanical energy. It might go to like permanent deformation, like if the car crunches up. About there was some force times distance that crumpled that car. And I phrase this as a change in kinetic energy, which would be true. That's how you would test it. But sometimes they phrase it change in mechanical energy. Look for change in kinetic energy. Right? So the sort of technical problem with this was that if you the previous question I left it like 3 digits, and if you took that, which is slightly rounded, and you did the calculations with kinetic energy, the fact that it was squared and there were differences of squares. The rounding error, even if it was off by like 1 part in 1,000, it was enough to blow up the change enough that it was kind of ambiguous as to what the multiple choice answer would be. So that was like, oh boy, that's why here's my my rewrite. See how I did like a ridiculous number of digits, right? Because it's like rounding on top of rounding. So actually, this might be a good problem to ask in the future in terms of variables, right? Because it'd be better than like numbers, right? That's one. But then that was the sort of technical calculator type problem. But there was actually a much more fundamental problem. I was like, oh, wow, I actually have to go back and like rewrite the numbers to that question. Right? What was like fundamentally wrong with number 6 and 7? Yeah.
With mine, it actually went up in kinetic energy. Yeah.
Oh, yeah. You guys got that? You guys got that? Yeah. Yeah. There was actually an increase in kinetic energy. Oops. All right. So yeah, I got my negatives all mismatched because I said I phrased this as how much energy was kinetic energy was lost, and then I calculated it. Final minus initial, which would represent a change, which should have been negative, which oops. Okay. So we gotta write this up because I do have a couple late entries, but it doesn't matter anyway because I'm omitting number 7. So here's how you would solve this. Just this here. You do sum of kinetic initial, right, which would be 1/2 mass of the first car, initial velocity of the first car squared plus 1/2 mvvb not squared. Okay. Then you do sum of kinetic energy final, 1/2 mass of the first car, velocity first car after collision squared plus 1/2 mvvb final squared. Okay. And then no, I know you guys just told me, but just make sure if I'm comparing kinetic final compared to kinetic initial, which should be the greater number of joules? Initial should be greater than final. Okay. So in terms of momentum conservation, there's time symmetry. So if you're not paying that close attention, it works either way. Yeah. So momentum before equals momentum after. But if you're doing this energy analysis, like, well, what was the change in kinetic energy? Right, this condition has to be true because that can tell you some order of some time order. Yeah, and I got everybody's exactly the wrong time order because that was a yeah, because I missed that detail. Right, so I had to go back and change the change the speeds of the cars to make a situation where the kinetic energy would decrease. Yeah, so totally fundamentally missed that, but really, at least in terms of the process you would use, you get like a number that makes sense for number 6. So I'll keep number 6, even though technically it's physically impossible. Okay. All right. You guys got that? All right. And so let's from this, you guys get to learn about all these principles. We switch the screen over, set the lights, get all theatrical. All right, so share screen 2, bump this, pull up this PowerPoint. And here we go, materials and states of matter. All right, so talking a little bit about scaling here. So when you scale something up, if you increase by some linear factor, I'll call it like x naught. Well, there are other size properties that change too, but in different ways. So here, let's say start with, do you guys see that the big cube is composed of 27 small cubes, right? 3 by 3 by 3. You guys see that, right? Okay. Let's start with the small cube. And let's say you walk around the perimeter. It's like some distance, right? And then you blow this up to the big cube. And then you walk around that perimeter. How much further around the perimeter would you walk around the big cube compared to the small one? I mean, I think it'd be a factor of 3 because you guys see a linear expansion of factor of 3. Yeah, it actually would be 3 times the perimeter, right, to walk around it. So anything that's linear, because the fact that there's a scaled up by a linear factor of 3, anything that's linear would also be a factor of 3, including like perimeter. Right? What about surface area? What if you wanted to paint? What if you painted the small cube? It takes like so much paint, like 1 unit of paint to paint the small cube. Now you're going to paint that big cube. How much more paint do you need to paint the big cube? It's not 3 times as much. It's how many times as much? 9 times, because paint's a 2-dimensional, or surface area is a 2-dimensional concept. So you have to take that linear factor and square it. I use lambda just randomly. I could have used k or anything else. I don't know. I pick lambda, just whatever. So 3 squared is 9. Okay. And then how about volume? So if you fill each box with water, well, it should be like 27 times the volume, right? So linear factor of 3, but then length times width times height. So 3 by 3 by 3. It's 3 to the power of 3 because 3 dimensions. Okay. Also, mass would go up by a factor of 27. Weight would go up by a factor of 27 because mass occupies volume, right? So yeah, so when you scale things up, like if you grew to like twice your height, let me stick with my factor examples here, right? If you grew to 3 times your height, say little kid to adult, if you grew 3 times your height, you would have 9 times your surface area, and you would have 27 times your mass and 27 times your weight, right? Approximately, if you were scaled up, exactly, right? All right, so a couple that just didn't play there. Let me dig in this folder, see if I'll show you here. Actually, we're just gonna keep going. We're gonna keep going. All right, so yeah. Okay. All right, let's look at thermal expansion. All right, thermal expansion. Do you guys know here? Let's skip forward. Did I not have where's my thermal expansion slide? Really? It's not here. Nope, I missed it somewhere. All right. I think I got a poster here I can dig up. All right. Here we go. Let me switch my screen over. Some videos start playing. Okay. All right. You guys know if you heat up an object, it'll expand. No, there are a few exceptions. So like water, if you go from a liquid state to a solid state, that'll be like decreased temperature. Well, that's an expansion, but that's a weird one. Okay? Most materials, you heat them up, they expand. But how much do they expand? Well, it depends on the material. It depends on something called this coefficient of thermal expansion. So here we go. If you had some initial length, L naught, and you change the temperature by some amount, now whatever temperature scale you use, doesn't matter because we're talking about temperature change. So like a change in 3 degrees Celsius, same as a change in 3 Kelvin. Okay. Then it will expand by some amount delta L. How much? Well, it's on the material. So alpha in this context is called coefficient of thermal expansion. Here's different coefficients of thermal expansion for different materials. You might notice that steel and concrete have basically the same coefficient of thermal expansion, which allows for steel reinforced concrete to be made. So I'll talk about that in the future too. Share my screen back over here. Now, what if you were to heat up this ring? Let's say you heat it up uniformly, right? Now the metal part, let's say it's like a metal ring, right? Metal part's going to expand. What about the hole in the middle? Does the hole in the middle itself get smaller, bigger, or stay the same size? We see show hands what you guys are thinking. You may think that the hole in the middle itself gets smaller. Who says smaller? Who says the hole in the middle itself is going to get bigger? Who says it's going to stay the same size? Check this out. This one I got lined up for you guys.
See, right now, it goes through.
Barely.
With a little effort, it goes through, yeah?
It's not fit.
I'm not gonna take the time to heat up the ball. I'd waste your time, because you know the ball would get bigger and no way it would go through. I'm gonna heat instead the ring. You get that ring nice and hot. Is the ring expanding? Yeah, it's expanding. How about the hole? Is the hole expanding? See, a lot of people think this. A lot of people reason that the hole is it's gonna expand this way and expand in this way because the ring is gonna get fatter. Will that ring get fatter? Turns out it will. So they think this part will expand out here, and this part in here, and the hole gets smaller. But lo and behold, appreciably bigger. So the hole does get bigger again. If we take our ring and we cut it up into 4 pieces, gang. 4 pieces. And if I put any one of those pieces on the oven, would it get bigger? Would it expand and maybe look like this? No way. It's going to expand and look like that. And this side here is longer in an expanded state than like this. So take them apart and look at it and you can kind of see it. Or take your ring and open it up like this. Is it going to get fatter? Yes, it's going to get fatter. So it expands out to here maybe. Out to here maybe, yeah? But that's not the end of the story. You see, we're so busy thinking about what happens like this, huh? That we forget it's expanding this way too. And it expands lengthwise as well. And lengthwise, we see it expands out to here. I submit to you that this dotted line on the top is longer than this solid line below.
And then he has another example of this practical example. He says, let's say about like a glass jar with a metal lid. It's really tight, like you just can't pull it off. Well, if you put it under hot water in the faucet, right, then that lid will expand, and for the same reasons, it gets looser and it's easier to pop off. Right?
Hi gang, thermal expansion time. Here I have what's called the bimetallic strip. It's a strip of metal consisting of 2 kinds, brass on one side, steel on the other, welded together. I'm going to heat it up. Looks like it's bending. It's bending because one side's expanding more than the other. If I take this and turn it into a coil and heat it up, it would shrink, or cool it, it would expand. That would be a thermostat.
There you go, different coefficients of thermal expansion. Some of these videos were those. Okay. All right, next to Archimedes' principle. All right, so this is about buoyancy. Now, why does the buoyant force push you upward? I'll start with that. So why is the direction of the buoyant force upward? Well, it has to do with the fact that pressure is scaled linearly. I should have a pressure formula up here, but it's very similar to this bottom formula. So So if there's a pressure, it would go like this: pressure, like water pressure. You guys know if you dive into a pool, deeper you go, the more the pressure, right, is equal to the density of the fluid, like water, times the gravity field, times the depth that you dive. So if you just replace this volume with like depth, like H depth into a pool, that would be equal to water pressure. So it's pressure is scaled linearly. So if you dive twice as deep down into the pool, you feel twice the water pressure. Right? And okay, well, if objects are 3-dimensional, then that means that there's some height change for an object. That means there's a little bit more pressure on the bottom than the top. Right? And then pressure times area results in a force. That's why the direction of the buoyant force is upward. Okay? Hey, how about this? In this room right now, is the atmospheric pressure on the floor more than the atmospheric pressure on the ceiling? Yeah. Do you think that difference is enough for it to be significant for any reason? Huh. How about this? What if I had a helium balloon that was like about 1 foot in diameter? Helium balloon. Right? I let that balloon go. It's going to rise straight up because the atmospheric pressure is actually a little bit more on the bottom than the top. And that difference is enough to make the balloon rise, able to actually overcome the weight of the helium balloon and material holding together. Right? Right. So that's the direction of the buoyant force. That's why it's upward. Right now, how can you quantify the magnitude of the buoyant force? There's a fun story with this. You guys probably know the story. This guy Archimedes, he was tasked with trying to figure out. Here's how the story goes. There's this. Wait, did I tell you guys about the Eureka story? Probably did. Yeah, there was that one day we had no internet, right? Okay, you guys remember that, right? So they're trying to figure out, is this crown made of gold? Well, if we could figure out its density, well, we can get its mass, but how do we get its volume? Well, submerge it in water, and then that water level change. We can see something like that, right? Right. So leads to this. You could say the magnitude of that buoyant force is equal to the density, not of the object, but the force acting on, but of the surrounding fluid. Right? Back up. I don't want to get this yet. Right? Start top line. The weight of the displaced fluid. Right? So if you dunk this object in this water, okay, it's displacing some amount of water. Do you guys see how the force rating on the scale decreases by 3 newtons from 4 down to 1? Right? Ooh, does that indicate like a buoyant force of 3 newtons, like sort of support force from the water, right? Like 3 newtons? Right? And if you capture that water, like overflow, it would also be a weight of 3 newtons of water. Right? So that's what this top line says. Right? The weight of that displaced fluid is equivalent to buoyant force. Right now to the bottom line. Right? Here's where we get a bit more granular. If you take the density of the fluid times the volume of displaced fluid, doesn't that represent the mass of that displaced fluid? Right, rho times v. Right? And then mass times gravity field. Oh, well, that's like a force, like a weight, right? Like a force. Okay, so there you go. There's the magnitude of that. I want to show you the Paul Hewitt version of this too. It's this one.
What I'm going to do.
All right, it takes a while to set this up. You guys see that object weighs about 10 newtons. I think it's 1 kilogram. Right? So 10 newtons. Right? They dunked in water and see how it went down to 6. So see, it lost 4 newtons of weight. Right. Right. Then it's going to read this thing.
Water.
Right. And then he's going to. Do you guys see a straw right here? It's going to catch in the speaker. Now he does. Some of that water just spilled out, so he just lost like about a half Newton of water right there. So that aside, right, he's going to catch that beaker. Now the beaker itself weighs about a Newton. Right? You guys see it weighs about a Newton, right? And then as he lowers this one into this red water, you guys see this red water is filling up the beaker over here, right? So what's the end result of this? Go to about here. You guys see this one has lost 10 down to 6, was like a loss of 4. This one went from 1 up to almost 5, but he lost a little bit of water, so we'll call it 5. It also gained 4 newtons, right? So see that difference there? All right, so that is exactly what this is showing right here. Okay, what can you do with Archimedes' principle? There's a problem I like to solve in my honors classes of trying to figure out what % of a floating object would be submerged. Right? And this would be the first step. You say, okay, well, there's 2 forces on this iceberg. There's the weight pulling down, and there's the buoyant force acting up. So mass of the iceberg is density of the ice times the volume of the ice, and that counts for the entire volume of the iceberg times gravity field. And the buoyant force, well, that's rho GV, but the rho is the density of the seawater, right, times gravity field times the displaced volume, which is only the volume of the water that's being pushed out of the way, like the submerged part. Okay? And you can set those equal to each other and then find the ratio of what is the submerged volume compared to the entire volume. Right? So that's how you solve that one. Okay? Side note here, it kind of bothers me. That iceberg is actually not in stable equilibrium, although it's hard to find one because everyone, that's obviously not a picture, that's just an animation. everybody draws their icebergs and not stable equilibrium. I don't know why. That would very quickly just turn over outside, but yeah, a little detail there. Right, Pascal's principle. Right, so this one, oops, trying to match the picture for the, hey, where's my Pascal? Oh, maybe I don't have a poster for Pascal's. Oops, sorry if you're at home. It's a tiny thumbnail anyway. Okay, so the fact that fluids will transmit pressure undiminished lets you create something like this hydraulic lift. Now you might say, well, maybe there's a tiny bit more pressure on the bottom than the top. Like as you go deeper, there's a little bit more pressure. Okay, that would be true, but you could definitely say this: there's equal pressures at equal elevations. Even if you get up into like this piston and this piston at equal elevations, there's equal pressures. Well, if there's an approximately equal pressure, maybe slight height differences, right, on each piston from the bottom, right, same pressure. And you guys remember pressure is force per unit area. You can rearrange that and say, well, a force would be a pressure times an area, right? All right. Well, if that's true, then remember, these are equal pressures, same pressure on both sides, bottom of the pistons. If I apply a small force on the left side to the small area piston, okay, I can get output on the other side on this large area piston. A large output force. So with a very small input force, you can lift something very heavy. Do you guys remember your pulley systems last semester? Right? This reminds me a lot of that. Like there's a mechanical advantage involved, but there was a catch. There's a way that you pay for your increased strength, your mechanical advantage, and that was to pull lots and lots of string. You guys remember that? Very similar thing here. Here, there's equal volumes of fluid displaced on both sides. And because small cross-sectional area versus large cross-sectional area, that means you have to push down a very large distance just to lift the car a very small distance, right? So you can only lift the car a little bit, but at least you can lift it, right? At least you do get a mechanical advantage from that. There you go. There's hydraulic lift from Pascal's principle. Right. Next, okay. This slide, there's actually two ideas put together. But what's the story here? The story is I got a fluid flowing through a pipe system, and maybe the cross-sectional area of the pipe system is changing. Okay? There actually is a photograph right here of that happening right here. It's going to lead to this idea called Venturi effect eventually. Right? So we've got this fluid flowing, cross-sectional area is changing. I'm going to start with this one here, conservation of flow. So would you guys think that the volume per time is probably pretty consistent throughout the system, especially if it's a liquid? Right, specifically, right, like the gallons per minute or cubic meters per second would be the same everywhere in the system. Now, if that's true, volume per time, you can rearrange that. Volume per time, is that like cubic meters per second? Well, take a look at this cross-sectional area times velocity. That would be, see, square meters times meters per second. Oh, that's also cubic meters per second, isn't it? So you can derive this conservation of flow from the fact that, there is conservation of flow. You can get cross-sectional area times velocity is that product is consistent everywhere in the system. Okay? Now, if that's true, what that means is that for the smaller cross-sectional area is let's call this water in here. Is this water moving faster or slower? For the smaller cross-sectional area, the water moves how? Faster, right? Here, example numbers, 10 times 10, that'd be 100 cubic meters per second. Right? That might be equal to like 5 times 20, right? If you have half the cross-sectional area, you have double the speed. You guys that? Okay. And that sets up something else pretty interesting. There's actually a resulting pressure change. Now imagine that you're a fish swimming around inside this pipe system. If you go from the big pipe to the little pipe, you actually feel a pressure change, almost as if you had changed elevation in the pool. Right? Now, how does that pressure change? Well, that leads to Bernoulli's principle, which is this very top line here. You guys see Bernoulli principle? Right? Does that look a lot like conservation of energy? You can actually derive this from conservation of energy, but it's just in pressure units. So if you have, this looks like kinetic energy, 1/2 mv squared, potential energy, mgh. And then you might have other types of energy. You might have some general E for energy. Right? And then if you divide all 6 terms by volume, you get pressure units. This represents internal pressure, and then pressure units due to motion, pressure units due to like height. Right? You know, if you go down the swimming pool, feel a pressure change, right? And that sum has to be conserved in a closed system. Right? You can add complications onto those. I mean, like anything in this class, right? When you consider, well, maybe there's like some shear force that's, some frictional force with the walls of the pipe. We're ignoring all that, right? We're just saying everything is conserved, right? So simplified a little bit, but like most things in this class, right? Right. So what that means is that, if there's a height change, obviously there's an internal pressure change, but you would know that already. But also if there's a speed change, there's an internal pressure change. Oh, see if you guys can predict this, and then we'll navigate the equation, see how this works. You guys see this paper, I'm just holding like this. I'm gonna blow a stream of air over the top. Wouldn't that be like a fast moving fluid? Now, a fast moving fluid, do you think that corresponds with a high pressure that would push this paper down, or a low pressure that would vacuum this paper up? What do you guys think? How many of you guys think that fast moving fluid is gonna result in a high pressure and push us down? Who thinks that? Who thinks low pressure is gonna vacuum it up? Yeah, maybe kind of like this hose right here. This hose right here, kind of give it away. It's on the screen here. Let's see. Let's do some signing in. Ah, do you guys see that? It does vacuum the paper up, which indicates a low pressure. Okay, so moving fluids are associated with low pressure. Now, why would that be? Well, let's go back and navigate this. Let's say this is like 10 plus 10 plus 10 equals, right? So 10 plus 10 plus 10 would be like 30, maybe pascals or something, right? All right, well, if the water has to speed up to maintain conservation of flow in the small pipe, that means that this term right here would be more than 10 units. I don't know, maybe it's like 15 units, for example, right? And if there's no height change, because this is just a horizontal pipe, just simplified, right? Then this term is equal to this term, so that means 10 and 10. Well, if I have 10 plus 10 plus 10 equals, okay, this might be like 5 plus 15 plus 10. You guys see that? Right? Do you guys see the internal pressure would have gone down? Right? Exactly consistent with the experiment that I just did, right? Like vacuums the paper up. One classic example of Bernoulli's principle in action is it contributes to lift for an airplane. So the wing of a plane and the entire top of the plane is designed to have more surface area than the bottom of the wing and the bottom of the plane. Right? Now, how does that contribute to lift? Well, because as the plane is cut through the atmosphere, cut through air, the larger surface area on top means that the air on top actually has to move faster over the top than the bottom. If it has to move faster, that means there's less pressure on the top. All right, there you go. You got some lift. Also, they tilt the wing a little bit. That contributes to lift too, but Bernoulli principle is one contribution to lift. Right? And also, I got a couple of images on the right side called Venturi effect. One of these is an actual photograph. Let's look at that one. You guys see two different fluids? I don't know what those are. I'm going to call it oil and water, but I don't know. It's two different fluids. You guys see that oil on the top? Now, they have it flowing right to left, but it doesn't really matter. It could be flowing left to right, and you see the exact same picture. But it does have to be flowing. Right? The fact that it's flowing faster in the small pipe means that there's a lower pressure in the small pipe, and you can see that pressure differential right here. You guys see it, that pressure differential manifest right here. So fast moving fluids, lower pressure. You get airplane lift, you get Venturi effect. Hey, do you think you could get the water moving so fast? Did I show you guys what happens to water at low pressures? What it boils? Yeah, you guys remember that from yesterday? Okay. Do you think that water could go so fast, the pressure drops so much that the water starts to boil? There's a term for that. It's called cavitation. So here's a pump system where there's a restriction, and these cavitation bubbles are actually destroying the internal workings of that pump. Yeah, so there you go, cavitation. Bernoulli's principle, get a special for that. Right, let's look at states of matter and state changes. So you guys know three main phases that you see. Room temperature on Earth could be like solid, liquid, and gas. You guys know, and water is one of the substances where you can commonly see it in all three phases, right? Solid, liquid, and gas. But those aren't the only states of matter, right? There's also, you could go to, if you heat up a gas enough, you can actually strip the electrons from the nuclei that they're orbiting. So that's called a plasma. Show you guys some examples of that. Actually, when I flip on the lights, these fluorescent lights, that's actually a plasma, right? There's like ionized gas inside those bulbs. Okay? If you can actually get this hot enough that the atoms themselves actually disintegrate, like the very beginning of the universe, like maybe like the first, I don't know, so many years of the universe. I think it's like 380,000 years of the universe. I might be wrong on that detail. Yet there was like no atoms that existed because it was just too hot, right? The matter of the universe was just too condensed. Right? So yeah, there's stuff beyond plasma. We'll just stop at plasma, right? You can actually go the other way too. If you cool a solid enough, you can make a solid cold enough that the internal structure of the atoms actually disintegrates the other way, and you get something called a Bose-Einstein condensate. Say, here we go. Okay, so here we're looking at different examples of plasmas. I got a bunch of plasmas here. Ooh, lightning, neon signs. Right. right? The sun. Right? You can create plasma in your microwave. It's a fun experiment with a grape. Right, where's this grape experiment? Here we go. The grape. Okay. Play my grape. Yeah, here we go. All right, so if you take a grape and split it in half and leave the two parts connected. Actually, I've seen two people do this with like just a couple of grapes and leave them in contact with each other, maybe like a shallow sloped bowl. Right? And then notice they took the turntable out. So they're just stuck in one place, right? They also threw a glass over this so they could capture that plasma ball. Right? The reason this works is because the diameter of the grape is a factor of the length of the microwave that's being sent across the oven, and it will set up a standing wave. Right? There'll be resonance, and it'll amplify a bunch of energy all in one place, so you get a plasma ball. Yeah, you can capture just like that. Right. Some other examples of plasma. You guys just saw a bunch of examples. Right, there you go. Fluorescent lights, neon lights, plasma balls. There's a technology application of this they give. There's an example near the end too. So let's look at that.
All of these different colors are specific to the gas chemistries. Plasmas can be used as a controllable reactive gas. So for example, if we put an object at the edge of a plasma, the charged particles will bombard the object, etching away at the surface. The electronics industry has used this concept to make smaller and smaller atoms into silicon, which is used in laptop computers, cell phones, and a whole wide variety of other applications. Plasma processing proved essential to the rapid miniaturization and increased performance of computers. These plasma processes are integral to the information revolution that is occurring today. Here at the University of Maryland, scientific research will continue to advance our understanding of plasma and its applications to make it better.
June the 5th, 1995 turned out to be a big day of the
Okay, let's go the other way. Let's get super cold, right close to absolute zero.
history of physics. They had finally made what Einstein had predicted 70 years before, a Bose-Einstein condensate.
Our first reaction was, wait, we got to be careful here. You know, let's think of all the different knobs we can turn, checks we can make, and so on, to see if this really is Bose-Einstein condensation.
A condensate is sort of like a vampire. If the sunlight even once falls on it, it's dead. And so its realm is the realm of the dark. But we can take pictures of them because we strobe the laser light really fast. And even as the condensate's dying, it casts a shadow, and the shadow is frozen in the film.
Wyman and Cornell created the first Bose-Einstein condensate in a cloud of just 3,000 atoms of rubidium, the first in the universe, as far as we know. They had reached a temperature of 170 billionth of a degree above absolute zero.
Yeah, so it's tiny, tiny, tiny fraction of a degree above absolute zero. When you get to low temperatures, other weird stuff happens too. So here's some helium that they're lowering the temperature, and it's boiling away, but they're getting it, you say here, like 2 Kelvin of absolute zero. All right. So what's going to happen with this helium?
Liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomenon in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity.
Ooh, yeah, a frictionless fountain that never stops flowing. That's crazy, right? And then he just mentioned there superconductivity, which is a similar idea with electricity. If you get temperatures low enough, you can get superconductivity. Where you can show if a wire gets colder and colder, the conductivity increases, so electricity flows better. But there's a cutoff point. It depends on what material you work with, copper wire or what material wire. But there's a temperature where it'll just like drop off, and there will be absolutely zero resistance at all. And yeah, so you get superconductivity, and then with that you can do some cool things too. But the trouble with these things, even though they're like super cool because there's like zero friction, they could just like run forever. Trouble is that these only happen at crazy cold temperatures. So I mean, not really Bose-Einstein condensate example, but just there's these critical temperatures that are really low where you get these like really weird properties. Right here. All right, so did these? Oh, okay. Then there's these. I give you guys the cornstarch and water, right? So you guys saw this one? Got the pull of that. All right, so there's these weird materials that are, it's hard to classify exactly. Like, is it a liquid exactly? Is it a solid? It has a little bit of properties of both. There's also something called a supercritical fluid, where I bet this is. Okay. We go back to this one right here. Okay. Whoops, stop sharing my screen. All right, so you guys remember this from yesterday. So we got increasing pressure going up, logarithmically scale, increasing temperature going to the right, that's linear scale. Right? And these different phases now this is for water specifically. Each chemical might have a similar looking phase diagram. But there's actually it's right here at the edge of the critical point between liquid and vapor. So if you go any higher temperature from this point, it's actually ambiguous as to whether it's a liquid or a vapor. And so yeah, it of course is very high pressure also. It's a very high pressure temperatures. There's actually ambiguity between those two states of matter. So let's say let's flash through these real fast. Okay, so you got components of our atmosphere, mostly nitrogen, some oxygen, argon, trace amounts of other things. We did scaling, the expansion. You guys saw pressure volume. You guys saw Archimedes principle, Bernoulli principle. I don't have a Christopher Pascal's principle. We make one for next year. Okay. Engineering, stress and strain. We'll talk about phase changes. All right, so I guess all of those things. All right. We get lights on here, and we're going to solve a few problems. Guys, we're ready for lights? Like lights. All right, so actually, I'm glad we have a few minutes here because I wanted to do a temperature conversion with you guys. Temperature conversion. I know I showed you guys some temperature scales yesterday, but let's say you vacation in some country in Europe and say, oh, it's 21 degrees outside. You're like wait, what? What is that in American? So how do you convert from Celsius to Fahrenheit? Yeah, 9/5. Okay, so the temperature in Fahrenheit would be the given temperature in Celsius. So this is it's 21 degrees outside. Like what? But yeah, you're right, 9/5. Okay, so it's scaled by a factor of 9/5. Now, and then plus what? 32. Yeah, good call. And even if you had never seen this before, I bet you guys could figure out that this would be plus 32 because you guys know that the freezing or melting point of ice or water would be 0 degrees Celsius or 32 degrees Fahrenheit. So if you plug in 0 for the Celsius number, that must be corresponding to 32 Fahrenheit. And the only way to get that is to tag on 32 at the end. You see it? Now 9/5, that's very close to what integer? 2, right? But 2 would be overestimating a little bit, like rounding up a little bit. And then because it's like 1.8, right? It's almost 2. And then if you round this down a little bit to 30, you can get a pretty good estimate that you could just quick calculation in your head. Let's try the 21 degrees example. So 21 times 2 would be 42 plus 30. That's like 72. Right. So I might say, okay, about 72 degrees Fahrenheit. Okay. Let's see what exactly 21 degrees Celsius is. So if I plug in 21 degrees Celsius, so 9/5 times 21 degrees Celsius plus 32. What did I say the estimate was? 72. So no, 42, oh yeah, 72, let's see. Oh, it's like about 70. Okay, so the land's really close, right? Like I said, degrees Fahrenheit. And so, and of course, if you had Fahrenheit, you want to go back to Celsius, you could just do some algebra and rearrange it that way too. If you want. How do you go from Celsius to Kelvin? The temperature in Kelvin is equal to the temperature at Celsius. Finish this equation.
Just be like Kelvin minus a lot.
Yeah, what is a lot?
270 something.
273? Yeah, 270. Yeah, you guys say 273. Okay, and then like point something, but right, basically 273. Sometimes I say K equals C plus 273, right? So if you said 21 degrees Celsius, right? So what would that be in Kelvin? 21 degrees Celsius plus 273. That's about 294 Kelvin. And yesterday I showed you that you would have to know that specifically for some applications like ideal gas law. If you're like scaling up or down temperature by some factor, you have to work in Kelvin, absolute scale. Or if you want to calculate entropy, right? Like how much entropy increase from some thermodynamic process, right? Something like that. Right. So there's a couple of those. Right, let's solve the iceberg question. Yeah, kind of time for that. Right, so you guys saw this set up diagram, but say there's this iceberg floating. You guys ever hear if you see an iceberg floating, how much percent is actually above the surface? Yeah, about 10%. Right, you guys probably heard that. Right. Let's prove that. Let's derive that. Right, so I got this iceberg. I think there's two forces on it. There's its own weight, which is the mass of the iceberg times gravity field. Okay? And there's a buoyant force, which I showed you Archimedes' principle is equal to, well, I'll say buoyant force is equal to density of, not of the ice, but of the surrounding water, right? Times gravity field times volume displaced. Okay. Now take these two outside pieces, density of the water times the volume displaced. That would be the mass of water if it were to occupy this here hatched in volume. Like if you took the iceberg out and this is a void, filled it with water and took the mass of the water, and then times gravity field, that'd be like the weight of that action, but not of the ice, but of the water. Right? Okay, so I can say that those two would be equal to each other, right? So if the sum of the force equals 0, this plus this zeroes out. So these magnitudes are equal. So how am I do this? Density of water times gravity field times volume displaced is equal to mass of the ice times gravity. Right? Now I'm going to rewrite the mass of the iceberg in terms of its own density and volume. So density of water, gravity field, volume displaced is equal to density of the ice times the volume of the entire iceberg times gravity field. Is that true? Is that right? Oh, do you guys see the G cancels out? Okay. And now, whenever you see a variable cancel in physics, pause and think like what that means. That means that whatever the answer to this question is, like what percentage is submerged or above, right? Would be the same regardless of what planet you're on. Right? You can take this whole materials to like Mars, and the same percentage would be like floating. Okay. Now, what we're solving for is actually none of these four variables specifically. We're looking for a ratio. For example, how about this? Displaced volume compared to the entire volume of the iceberg. That's equal to density of the ice divided by density of water. Okay, so the percent submerged, this is what percent submerged is, right? Is actually just equal to the ratios of the densities of the materials. Density of ice, maybe like 9, I'm gonna make up a number that's probably pretty close. Maybe like 925, maybe it depends if it has like air pockets or dirt mixed in. But I'll call it 925 kilogram per cubic meter. Density of fresh water would be an even 1,000, but maybe salt water might be like a little over 1,000. Maybe I'll call it like 1025, maybe something like that. Okay, so there's the ratios of the densities, kilogram per cubic meter, the units cancel out. And what do we got here? We got, ooh, do you guys see 90%? Right, so sort of made up some numbers on the fly, kind of rounding a little bit, but yeah, about 90%. So there you go. So 90% of the volume of that iceberg would be underneath, and 10% therefore would be above. Is that? All right. Actually, I think that worked out pretty good. Covered stuff I want to cover. All right, so tomorrow we'll do nuclear engineering, civil engineering. Yeah, so fun times ahead. Right, and then we'll start electricity into this week, and then we'll take next week to do electricity, and then after that, we'll go back to review unit 6, some power line motion, unit 7, rotational dynamics, and then do some practice exams. Again, if you guys want to do extra practice on your own at home, there's lots of resources open on AP Classroom. So you guys know that too.